So this is Brian Kiedrowski. Brian and I went to grad school together at the University of Wisconsin. He was a couple of years ahead of me, but he did his PhD with Paul Wilson. And a lot of his work was also in collaboration with Los Alamos National Laboratory, which is where he went to work immediately after graduate school. And he did awesome work there, mostly Monte Carlo methods. And now he's a professor at Michigan. So he's going to tell us about Monte Carlo methods. And it's really a pleasure to get to introduce him because I've known Brian for so long and we've got to see sort of our careers.
A very similar path, actually.
Yeah. So without further ado.
Thank you very much, Rachel. All right, welcome everyone. I'm Brian. So I'm going to talk to you about a couple, I'd say they're randomly selected, but it was a fair to me random number generator used to talk about these transport methods in my research group. So I have a research group here, various things going on. You have Monte Carlo method, which is using random numbers to solve the neutron transport equation. By the way, I love the neutron transport equation, my favorite equation. They actually pay me to, well, I guess, watch other people solve it these days. So I also do a little bit with deterministic methods. I'm not an expert in that, but I also try to combine the two. So I've got a bunch of people working on this, and then I have a few non-proliferation related things with fission and fundamental physics models. So I'm going to focus on laser beams. Two topics here in bold: kernel density estimation and sensitivity methods, and something we call cost optimization, which is an alternative scheme for doing what's called variance reduction. If I say any foreign phrases to you, things that are out of the blue, well, feel free to stop me and I'll explain it as best I can. Okay, so this is a two-part talk, as I kind of implied. Cost optimization, Monte Carlo sensitivity analysis. So I guess I should say I'm getting paid by two groups. One is the Consortium for Nonproliferation Enabling Capabilities. It's one of the three nonproliferation consortia. It's run out of NC State. I'm actually not part of the Michigan consortia, interestingly enough, as well as Los Alamos. So that's my former employer, and they've been kind enough to basically take my students and help pay for doing their work. Okay, part one. Cost optimization with this funny variance reduction technique called DXTRAN. Okay, so in CNEC, we are trying to solve a hard problem. This is a CAD model of a city block in Ann Arbor. We're trying to run a radiation transport simulation on this, and we're trying to do it in an efficient manner. So we want a high fidelity. So oftentimes in non-proliferation, we use what are called low fidelity calculation. We need to benchmark those against high fidelity calculation. We actually solve the actual transport equation. It's geometrically large. You have localized source detectors. Source location may not be known. The detectors may be in motion. There's a lot of complications with that. The transport process is dominated by these stream paths, basically the streets, gaps between buildings. And consequently, because of the sheer size and just complex physics, there isn't really a good tool in our standard toolbox to solve this type of a problem. So since I'm a Monte Carlo person, I'm going to try to hit it with the Monte Carlo hammer. But in order to do this in any sense of an efficient way, I have to use something called variance reduction. So has everyone here heard of variance reduction? All right, well, I'm going to talk about it anyway if you haven't. It's okay. Okay, so Monte Carlo, the quick version is as follows. We're simulating the physics as it happens on an event-by-event basis. Radiation interactions, basic quantum mechanics, they're all random. So what we're interested in is the ensemble average of a bunch of radiation interactions, and we're telling that to tell us about the radiation. Okay? So this can produce very accurate results because we can represent physics with as much knowledge as we know about with very few approximations. But it's kind of a terrible method because it's computationally expensive. So anytime you're using random numbers to solve information, you got the curse of the central limit theorem, which means that convergence goes as 1 over the square root of the number of samples. So in other words, if I spend an hour to get a 20% uncertainty, if I want to get this down to 2%, I have to do 100 more hours of calculating, or 99. So it's n squared. So you pay the price for accuracy. Now, what we can do is we don't have to simulate the physics as it occurs. We can actually do things to the random walk that's going on in the simulations. We can bias it, and we can do it in ways that give you the right answer on average. So the problem with doing this is that you literally have almost infinite flexibility in how to do it. Now there's a limited set of techniques that we have that are actually shown to be effective. The problem is that their application, it can be a little bit more of an art than a science. So oftentimes people who apply this are really experienced, they have analyzed problems like this, and it's a lot of trial and error, so it's a lot of human time. And these days, human time is rather expensive and computer time is cheap, so we would like to use computers to try and get us to really good answers. So in the last, I'd say, 20 plus years or so, there's been a significant effort on using deterministic solutions that'll help guide this process toward picking the variance reduction techniques, picking the parameters that you use for this. Okay, so there's a method called Kata that was developed, I think, by about 20 years ago by, that's primarily used by Oak Ridge.
John Wagner.
John Wagner! Thank you, Rachel. Yeah, don't you hate it when that name just pops out of your head? I was going to say John Mattingly, but no, he's the person I work with. All right, so I think I would consider this the current state of the art. So what we do is we solve a low fidelity adjoint problem. And I'll talk a little bit more about what the adjoint function is in just a bit. It's the neutron transport equations even twin, if you want to think about it that way. And it's production capability in a code called Advantage, which basically generates biasing parameters for MC and P using the scale code package. It uses the de novo as the transport solver for this. Now, some of the limitations. First of all, in most implementations of this, there's no angular biasing. Now, I know Rachel's research group has been focusing on fixing that up, so there's been a few notable exceptions there. But by and large, the fact that you don't have any preference for particle directions can really hurt you in problems such that we're trying to solve here for where stream paths and directionality matters. Also, when you apply Kata, there's no consideration for how much time this is going to take. So what ends up happening in a lot of calculations is you end up what's called oversplitting and wasting a lot of computational effort. And I'll show an example of this on a source detector problem. Also, Kata has been developed for a specific technique called weights and source biasing, but there's a lot of other games out there that we can play that are biased and random walk. And it's not necessarily clear how you take the results out of Kata and apply them to those other techniques. So I'm going to show you one in particular called DXTRAN. Okay, so here's a source detector problem. So what I have here is reflecting boundary conditions. I've got a source in the lower left, a detector here, an optically thick shield, and air in between. So the problem's kind of ginned up to really exacerbate the physics, so where you have to go around the problem scattering through the air. It's a typical sky shine type problem is what we're doing here. So what I plotted here in the color map is something called the adjoint flux, produced from the deterministic calculation. Again, adjoint, what it is you think of it as if I plot the particle somewhere in phase space, let's say right here, this tells me what is the expected contribution of this detector. So if I plot one nearby, it's going to be high. If I plot one far away, it's probably going to be low on average. All right, so I use the adjoint solution with Advantage is the code out of scale, and it generates what are called lower weight window bounds. And what I have here is a typical history that actually contributes to this detector. So this is just taking one history and just plotting it. Where do the random walks go? So source is down here in the lower left corner. Goes up, bounces off. You have some splitting here as you go in more important regions. Then you get to a significantly more important region, and you get this cascade of copies of random walks that go through. Some of them bounce back out. And eventually a bunch make their way down the detector down here. So as you go from yellow colors down to green, down to blue, you tend to make duplicates and you reduce their what's called statistical weight to keep the game fair. Okay? So this, on average, you get about 13,000 tracks in this one history. So what we can do is we can plot a histogram of how many tracks per history, and a frequency plot here, I guess it's absolute frequency. So I ran 1 million histories. And here, 10 to the 0 is 1. So this represents the particles do not scatter. So anything in blue are histories that don't even contribute to our tally. In yellow here, or maize, so Michigan colors, are the histories that do score. So anything, the one and done's is about 90+% of the history is just, they're basically don't take you much time at all. And all of this in blue you can think of as just wasted effort really at the end of the day. Because you did a bunch of work, you didn't even get a single contribution to your detector. So now if you look at this distribution, notice that this is in log scale. So even the histories that do score, some of them take, well, the ones that do score range from a few hundred up to over 1 million particle tracks. So you have a wide dispersion in the number of histories. So this is, again, using the Kata methodology to generate weight limits. So there's a lot of cost savings that we can have here. So when I think about variance reduction, I like to visualize it this way. I want to go on what we're trying to do. So on the left here, I have the score kind of given history. And the dashed line here represents the average, so the value we're trying to get at. At the bottom here, I have the number of tracks for a given history. So our goal with variance reduction is we're trying to take this scoring distribution and smoosh it down to a little point or a delta function along this vertical line here. And we're trying to take this curve and we're trying to move it over to the left as far as we can. Okay, so it reduces the time and reduces the spread in the scores, which reduces the uncertainties that we have. All right, now the problem is variance reduction techniques, they tend to do one while hurting the other, so there's always this trade-off game that we're playing. And the question is, how do you do this optimally? Okay, well, one technique that you can do is something that's called cost optimization. So cost optimization is similar to what Cadis does, but it has additional things associated with it. So what we do is we solve something called the history score moment equations. And I'm not even going to write these out. They're just way too long. And you all don't want to have a wall of math at 4 in the afternoon. What we do is we write down a set of equations that describe the moments of the various transport processes. So it has our usual phase space, position, energy, direction, as well as what's called a statistical weight factor. So we have an augmented phase space. And then we can obtain the mean, which is basically the first one of these equations reduces just to the adjoint transport equation that we're all used, royal we here are all used to solving. We can also solve for the variance. So if we solve for M1, if we use M1, we can then use that as a source term to solve the M2 equations for the second moment, and then we can compute the variance. And we can also similarly compute the expected computation of time as well. And once we know the variance and the expected time, we can minimize this cost function here. So this is one over the Monte Carlo figure variance. So we're trying to minimize this using optimization techniques. So this has been done for weight windows and various report splitting. And we're applying it for the first time to a variance reduction technique called DXTRAN. It's one of the most, it's an MC&P as well as a few other transport codes. And it's one of the most obscure, counterintuitive variance reduction techniques out there that I find of the whole list out there, this is the one fewest people are familiar with, but it's actually very useful for the problems that we're solving. Okay. So DXTRAN, what it does is we surround a region of interest with some object, a sphere or box or something. And what this surface, or this box, sphere, what have you, this DXTRAN surface, it acts like a magnet for particle contribution. So as you're going through the random walk, you're pulling particles over to this part. You're doing it in a statistically fair way. All right, so let's do a clip art cartoon here to kind of illustrate how it works. It's very counterintuitive. All right, so here's my detector that I surround with the DXTRAN circle. And here's my source point. Okay, so right at a source emission, what I do is I randomly sample a direction on this circle. I then move a particle, I teleport it, if you will, to this region, introduce it right here, and I contribute to my tau. Okay, so that's not the source emission. I also do the exact same things at collisions. I sample a source point, teleport a particle over here, create it, and score to a tally. Now, to keep the game fair, and it's a little counterintuitive how this happens, and actually the proof isn't particularly easy, is if the normal random walk happens to hit the surface, it goes poof. It disappears, we terminate the random walk. And this allows us to preserve the right answer on average. Okay? So we're going to try to describe this transport process with deterministic methods. And it's actually kind of tricky how you do it. Okay, here's the math. Just so you know, my research group does math. I don't want to belabor this point, but we had to develop a new transition kernel for the DXTRAN process. So this one right here does the teleportation of particles. So if you're not in the DXTRAN sphere, this Dirac delta just moves you to a randomly sampled point on the DXTRAN sphere with some first flight attenuation reduction way with some biasing parameter we call beta. Okay, so I don't want to belabor the details, but there's some math on it. Now the normal random walk, we have to truncate the screening kernel. So this is the equation that describes the normal transport process moving from one position to the other. But we have to chop this off at the DXTRAN region. All right, so to illustrate this, let's do a 1D where we push particles out either left or right. The analog trading machine kernel, wherever we start it, you see is you just see exponential fall off. It's just standard e to the minus sigma fold x. Now when we do DXTRAN, we have a DXTRAN region from here to here in kind of slab geometry. If you're inside the DXTRAN region, everything's normal. But if you're outside, we have to lop off the tail of the exponential when it reaches the sphere, because any particle that happens to reach has to get killed off, basically. Okay. All right. So what we did is we implemented this in a discrete ordinance research code called COVERT. It stands for Cost Optimized Variance Reduction. I think it was developed by my friend C.J. Solomon, who is working with us as part of his dissertation work when he and I were students at Gonzales. So what it does, it solves the history's four-element equations for important split-ending wave windows and a few other similar techniques. So what our research project is, we took CJ's code and we had to heavily modify it to incorporate this DXTRAN process. And why DXTRAN is because we've got a geometrically large problem, we want to pull particle contribution to a specific point in space. So that's why we're doing this problem. So I don't want to get dragged down into all the details of the iterations, but it requires special sweeps to develop this new boundary source that we have to do. Okay, that'll be a talk in and of itself here. All right, so I'm just going to jump to some cool looking results.
A question.
Sure.
Why you pick SN? There are more convenient methods that already do ray tracing.
Partly was the pragmatic reason we had the code set up with COVERT specifically that was using SN.
But you have to heavily modify it, meaning that it wasn't set up for this particular problem.
Yeah, so it's the one we had a code that was tested, and it's the one we ultimately went with. And I agree, there are better ways out there.
MOC and collision probabilities are ray tracing type of integral transport, very similar to what you are trying to do with Monte Carlo.
How well did they extend to 3D, however?
3D as well?
Okay, because everything I've done with interval transfer has been 2D specifically.
Well, there is 3D.
Okay, excellent. Yeah, so this is the one we had. And CJ and I actually talked about doing
This
MLC.
is just suggestion.
Oh yeah, it's just, this is the one we had. And actually, to be honest, the real reason is because Los Alamos loves the SN method.
I know.
So,
but this is not the best method for this.
I agree. Yes, it's just, well, you have the paying customer and you give them what they want. So in addition to CNEC, there's other people at Los Alamos who have their own interests in DXTRAN specifically. Yeah. Okay. No, that's a very good point. I agree with you. Okay, so we did a few simple slab problems just to test out our idea. So first we did a pure absorber, where we have a simple isotropic boundary flux, and we have a leakage current tally at the beginning. So this is something we can actually write down a pencil paper solution for. So it's something that if you solve transport, you should start with this problem, because you can't get this right, you can't get anything right, transport-wise. Okay. Then we said, okay, let's throw in a little bit of scattering, so we made it a little bit more complicated. All right, so now let's put in even a little more complexity with different regions in space. And we also fiddled with this beta, some biasing parameter of how often you play the DXTRAN game. And then we said, all right, let's do an isotropic volume source and a volume track length tally as well. So put a nice pure absorber in the kind of couple of the source detector regions. All right, so these are our 4 test cases, and So first we said, all right, can we get the means or the adjoint flux? I mean, lo and behold, yes, we're capable of doing that. So one is perfect agreements. So with high accuracy, we can get the match MC and P's calculated means. All right, so the variance ratios are, they're within a few percent, so they're not quite this good, but they still tell us we're getting very close to the right answer. Now, we actually did recently find, like last week, we found a bug in the code, so we're going back, and Joel's going back and he's checking this out to see how these results change, if they do at all. Okay, so now to illustrate, geez, all right, I should have redid these, test this on the projector. So here's problem 2 with the scattering, and here this dashed line right here represents the solution we hope to get. So fortunately it doesn't show up on the projector, it shows it on my screen, but there's a gray line right here, and you get perfect agreement for the P absorber problem for the adjoint flux as we expect. We can thankfully kind of see it on this one. For M2, the second moment, we expect there to be a shift. So variance reductions, they always give you the advance wrong average, so you should always agree. So this dashed out line represents the calculated second moment, which is used to infer the variance. And gray represents the analog process. So I guess I should add there's a DXTRAN surface right here at x equal 8 centimeters. So mean matches up. M2 changes, we expect it to change when we compare it with MC. All right. So then we did test problem 3. The means also, they line up as well. You know, a little bit more of a complicated shape here as you would expect when you've got a pure absorber in the middle. And likewise, the M2s, they have a similar level of, it's close, but it's not, doesn't quite follow the same pattern. And you expect that it changes. Now, 1D results really, they can only tell us so much. So let's look at a 2D test case, because I think this is a little more insightful. So this is a 3-leg duct problem. So you have source particles here, they come through, they somehow make their way to the end of this problem. We put a little DXTRAN insert box right here at the end. So in this we have the adjoint flux. So as you can imagine, being the expected contribution, it's high right as you're leaking out of the duct, and then low as you go away. All right, M2 has a more interesting behavior to it. So you see these little peaks right here, right near the tally region. Now what these are telling us is this says where is the variance coming from. Now it turns out in this problem, you get large contributions, large being relative to your average, very large, for particles that happen to scatter right near the edge, right near the lip of this duct. And we'd like to try to eliminate those contributions. So it tells you where are the problem features in our variance reduction scheme. So you can use this information to do further optimizations by other techniques to kind of smooth these peaks out. So that's what M2 is kind of telling us. Where is the variance coming from? All right, so as I conclude part 1, the new DXTRAN kernels, we deduce those for the DXTRAN game. We have some implementation in SN. It means all agree, and the code shows promising results. Again, we found a bug, so we're going to investigate some disagreement with. It's all the M2. The M1s work just fine. It's just how we're handling this boundary source sweep. Found a little, some things amiss. I want to get too technical there. All right, so also next we have to implement the computational time estimates. This is basically the same as the adjoint flux. Use a profiler to profile the code you're using to say how much does each atomic step within the transport calculation take. And that becomes kind of like your cross sections, if you will, for your adjoint transport equation. And then we're going to perform optimization using standard techniques to develop some rules of thumb. How do you apply this kind of vague, counterintuitive technique in a lot of problems? All right. So I'm going to shift gears, I guess. Since I'm going to shift gears to basically a different topic entirely, are there any questions right now? Okay, no, good, excellent. You guys want me to be done, sweet. Okay, so Monte Carlo sensitivities to system dimensions is the next topic. So, yeah, chosen randomly, I swear. Okay, so what we're trying to do here is we're looking at geometric uncertainties and how they impact a solution. So to do this, we need to calculate sensitivities. Basically, how much does a system dimension matter to a specific response? So for us specifically, as far as CMAC, empirical observations by John Manning's group at NC State says that the geometric uncertainties of the buildings actually drive the largest uncertainties for the search models that they have. So the densities and those things, they really don't matter as much, which surprised me that they have such a big effect. So again, and also if we want to do uncertainty quantification for critical or subcritical swimmers that we use to benchmark our codes, and we want to get good estimates of the uncertainties, we want to apply Monte Carlo to this. And there's other applications, shielding or reactor problems as well. All right, so we're going to use Monte Carlo, and we're going to try to calculate what are called these sensitivities. How much does changing an interface affect a system response? So Tim Burke, who did the work, he has experience doing this with OpenMC. We did it for eigenvalue problems. Those are the harder class versus fixed source as far as these methods are concerned. So everything we're doing here should reduce down nicely to fixed source calculations. Okay, so interface sensitivity. You got two regions here. We're going to call this the minus side, and we're going to call this the plus side. They have their own cross sections. We want to know the impact of a small shift of the location. So that's what we're trying to use, and we're trying to use Monte Carlo perturbation theory to tell us this. Okay, so first, all right, sorry, math, it's unavoidable. Comes up in engineering. The relative derivative with respect to an interface location. We're calling this location G. So it's the relative derivative of a system response R with respect to B. Okay, the cross section here, this is a piecewise constant function. So capital thetas are heavy side functions. So in one region it's sigma minus, and another region it's sigma plus. All right, so as some of you might know, when you go take a derivative of this,
so your cross sections are dependent on space or constant?
They're dependent on space in a piecewise constant manner. So a long array. So I drew it kind of orthogonal to the axes, but along any array, they're a piecewise constant function space. It's not required, but it's going to make the subsequent math a lot easier. Okay, so we take the derivative, we get down from the heavy side down to a Dirac delta function. And whenever I see Dirac delta functions, I rejoice because usually math becomes a lot easier from this point forward. All right, so perturbation theory, if you've studied in your class, you'll probably recognize this results. The relative differential change in K can be described by psi here is your angular flux. This is the distribution of neutrons, proportional to that. And this accounts for the derivative in the total interaction rate, derivative in the scattering, derivative in the fission process because of this interface shift. Okay? And this side with a dagger on it, this is everyone's favorite function, the adjoint function that I talked about before. I'll give a little more detail on what it means for an eigenvalue just a little bit. All right. So we take our derivative back here with the Dirac delta function. We plug it into this, and I guess I should have said that these braces here are volume intervals, the volume over the entire plot. When we plug in Dirac delta functions, the volume integrals reduce the surface intervals over our perturbed surface. So you get a bunch of terms, and I split them out in a very specific way because this is how we're doing this in the Monte Carlo process. So the plus here, again, is events occurring for the material on the positive side, minus is for events occurring from the material on the negative side. So that's how you interpret this as well. Okay, so let's kind of describe how we handle these, because we have to handle these terms differently than we handle those terms. So I'm going to talk about the easy one first. So the first one, we can use very existing techniques. So whenever a particle in our Monte Carlo random walk across the surface, we know how to do a tally for the flux at a surface using surface crossing estimator. It's a well-known technique, and this is just the difference in the cross section. We can easily just look that up off the cross section tables. And then we have to weight this by this adjoint function, and for this we use what's called an iterated fission probability method. There's others out there to do this, and I'll give you kind of a feel for how this goes. So you have a particle across the surface, use the surface estimator here as you cross, and you multiply the contribution by the change in the total cross section. So this minus that. Okay. Now, if you've heard some of my talks before, you've probably seen this figure. Okay, so the adjoint function is the expected response for some hypothetical particle plunked into a system. Now, when we're in a reactor, an eigenvalue problem, or a critical system, you can think of this as follows. So, we have a nice critical assembly right here. I sweep out all the neutrons. And I have a bin of neutrons right here, and I take one and I plunk it in a reactor at a specific point in space, and give it a kick in energy in a specific direction. And then I walk away, drink my coffee, and then I come back and I say, all right, how many neutrons do I got in there after a long period of time? I write that number down. Sweep all the neutrons out, do this over and over and over again, and that average is proportional to the adjoint flux for that one point. Okay, so that's what the adjoint flux is in a reactor, and how you would measure it in quotes here. So events in the Monte Carlo walk are like putting a neutron in a reactor. We're just going to follow it from that point on. Just observe how many neutrons do you make in the future. All right, so we have to store our contributions that we make in one generation, and then multiply it by the population this chain produces after several iterations in the future. That becomes a weighting factor. Okay, so that's how we do it. How we find the adjoint flux and how we weight by it. Okay, so that's the first term. Standard techniques are going to work. The second term, it's not so easy, because the problem is we need to know what scattering and fission is occurring at the surface. Now, unfortunately, in Monte Carlo, we don't have any of those, or we have so few that it may as well be zero. The measure is zero. So how do you do that? Well, the approach that everyone else has taken, so it's in the 70s, there have been a few people who've tried this. It all involves simulating random walks. I even tried this 6 years ago, and it just got ridiculously expensive that I just said, you know what, this is just a bad idea. So Tim, he got his postdoc, and we were looking for a topic, and he did it on something called kernel density estimation. So we're able to apply this technique, and I'll talk about it in a little bit, to systematically use the collisions that occur nearby and do the importance weighting on those. So with a good weighting function. Because you can always say, I'm going to take them nearby approximately, and that works, but it's this kernel density estimation that makes it actually get reasonable results. Okay. So kernel density estimation, if you've taken a graduate level statistics course, you may have heard of it. It's a common technique used in probability and statistics to estimate unknown density functions. In the last, 10 years or so, there's been applications by various research groups, a handful of them, to do this for particle transport. So the idea is you use nearby events with some kernel function here, which is usually taken to be a parabola, because that's been proven to be the best one, and use nearby events to find a contribution at a center point here. All right? Okay, so the idea is as follows. So we draw this kernel function, it's a parabolic-like shape around that. We'll talk a little bit about the width, that's the secret sauce you have. And any event that happens within this support, you tally that multiplied by the weight function, and then you see what happens after that. So that gives you a importance weight. All right? Okay, so now, again, the secret sauce is how do you get this thing called the bandwidth? So I always said nearby. Well, what does nearby mean? It means you have to determine a width of this function. So if you pick one that's too large, you get an overly smooth solution. So basically you get the wrong answer. Pick one that's too small, you get a good answer, but you have so much variance in it, you can't tell how to get. So it's very important that you pick an acceptable bandwidth. So what people do is they minimize what's called the mean integrated square error, which is the square of the bias plus the variance. And then just make your calculation. Unfortunately, the bias is unknown, so some approximations are going to be required here to do this. So what we did is we used, the bias is also unfortunately a strongly energy-dependent function for neutrons. And Tim's dissertation work over the 4 years that he was in graduate school was developing things that allowed us to use kernel density estimates to calculate reaction rates, and we applied that to this. Okay, so that's a whole other talk as to how you do these energy dependent bandwidths in accurate yet not excruciatingly slow way. Okay, so we ran a bunch of problems in OpenMC using various benchmarks. So we have bare sphere of HEU, plutonium surrounded by a nice tungsten reflector shell. We perturbed the inner radius, the outer radius. Zeus, which is like a pancake of HEU surrounded by some various reflector materials. Did a few solution systems, an LEU fuel pin and an HEU fuel pin. So what we did is we did direct perturbation. Basically, you just do this using what's called central limits. So you perturb one end, you calculate K effective, you do it the other way, you calculate K effective, and you use the finite difference formula for the derivative. Okay, that gives you a reference answer. If you're small enough, it's a good approximation of the derivative. And then KDE, here are the results we get from the method. And more or less, you get agreement within a few percent. However, unfortunately, the one problem I was really hoping this would work on works for the non-proliferation problems, the one they're interested in. So at least we gave the sponsors kind of something there. But I was hoping it's like, can we do this on light water reaction? It turned out there's still some problems there. So LEU, fuel pin.
Is that just because there's so much thermal scattering?
Oh, all right. So yes, but even worse. So when you change the inner interface location, it's all resonance absorption. So it's all the effect is all of these very narrow energy bands. So it turns out that generating both reference results as well as these perturbation results took a long time. So it's not as efficient as I would like for thermal reactor type problems, unfortunately. Also, this problem was one of the Castle benchmarks, and these are under moderated systems, but they're close to critical moderation, so there's a lot of nonlinear effects as well going on. And we're using first order perturbation here, so we're trying to draw a line, and we can only crunch down so far because we can't run for months to get reference results. So there's nonlinear effects, and also we'd like to revisit some of our choices we made for handling the energy and bandwidth. So it got accurate absorption profiles globally. But now as we drill down to these very narrow energies where they all matter, it appears there's more work to be done there. So these are our two kind of hypotheses as to what's going on. So again, work in progress. All right, extensions. Well, we already applied this to reaction radiation kinetic parameter. Then way off here, we used your stuff, so it all works great. Actually, the LEU fuel pin, reaction rate ratios, and everything worked just fine. It was only K effective that actually was the problem. Anyway, we think it's all because the resonances matter so much, whereas global reaction rate, like fission to capture and things like those ratios, it all appeared to smear out incidentally. Okay, so I don't want to scoop Tim, so he's going to talk about this at Winter ANS, and we have an SNR that's been accepted. So yes, your work was used. It's great. It works like a champ. All right, we also want to demonstrate again, so we want to apply this to fixed source problems. So I'm going to have another student look at that, and then one of our new faculty wants it again. He's also looking at perturbations for the Boeing problem and fast reactors, and he came by, and we're hoping to look at some of that with this problem too, with the fast reactor Boeing problem, to get the effects of that for his calculations. Also, we'd like to go into higher order perturbation theory, so second derivatives as opposed to first derivatives. So hopefully we can get some estimate of these nonlinear effects. And right now the theory is for uniform shifts in the interface. I think doing it for non-uniform is going to work, but we haven't demonstrated it yet, so we'd like to try that out as well. All right, you guys have probably heard enough. So this is the random number generator I used to get the two topics. It's completely fair, I swear. Hope you all like XKCD. So thanks for listening. I'm going to be quiet now unless you have questions. You want to hear me yammer some more. Yeah, Rachel.
For getting the eigenvalue adjoint solution, what is the computational intensity for that process?
Well, it's a good question because there are various trade-offs you can do. So it's always the classic trade-off between speed and memory usage. So if you don't want to use a lot of memory, so that's kind of, so the method I did for my dissertation work, I picked the low memory but high variance route. So if you do that, you just use the existing random blocks, and you just have to store information in this original generation, which is, so basically you take the iterations, the cycles in your Monte Carlo calculation, you break them up into blocks that are one after the other, and you store stuff at the beginning, you compute stuff at the end, and use that as your multiplier. So there actually isn't much increase in computation. Now, you can also store stuff every generation, this overlapping thing, and that, you get better variance, but you pay for it with memory. So take your pick. And there's been other things that, other methods called clutch, which uses like a fission matrix that uses a kind of an adjoint on a discretized mesh. So part of the reason we didn't go that route early at Los Alamos is we wanted things that just worked, that didn't have any user intervention, no discretization error. And some problems you get away with doing it, but other ones that are a little more weird, you want something that's just going to give you the right answer, so to speak. So it's all the trade-offs that you get usually. Excellent question. Yeah.
Could you talk a little bit more about the uncertainties in the transport in the urban environment? Is that from the formats that you're using to build your models, or? Okay, so there's several uncertainties. So where do the uncertainties come from in geometry? Well, you get it from Google Maps, and Google Maps doesn't give you down to millimeter. Okay, you get it down to maybe, I don't know, a meter or so if you're trying to, if that. So that's where they come from, is, you can use satellite data, et cetera, but unless you get someone out there with a tape measure, you're not gonna get the very high fidelity measurement. They matter, actually. I was wondering about like LiDAR or other approaches that.
Yeah, for a specific one, you might be able to do it, but if you have, here's a generic,
Gotcha.
You want to do this quick,
Right.
and pull from pre-existing satellite data, then there's going to be these inherent uncertainties. And same's true with engineering. Any component you'll make, there's geometric tolerances. That's just the fact of manufacturing. Those have to be factored into your uncertainty analysis. And right now, the state of the art with benchmark analysis, they just by hand do the sensitivities and then they quantify them for you. Whereas we're trying to develop a more automatic way of doing it.
So when you say that geometric uncertainty might be more important than density, is it like you change the geometry keeping the same density, so you change the total masses in the system, or you preserve the masses and only change the geometry?
So for these problems, mass conservation, for these where you're doing particle transport through, I'd have to ask John for the exact details, whether you conserve mass or not, but unlike criticality, where you absolutely have to conserve mass and various other quantities, my impression I get is it isn't as important to conserve mass. Now, in either case, if you change, there are ways that you can change the locations and preserve the total mass, it turns out. Now, I have to ask John specific details as to what he did for all of this. So this is like the last few months he published these, he discussed these results. I won't say he published.
Is this related to finding the reactive sources in kind of urban environment?
Yep.
Yeah.
Yeah, exactly. And yeah, he said he had a student, they tried twiddling up the densities, twiddling down the densities, and it didn't make much of a difference in the source search algorithms, but when you change the size of the buildings, that's had a significant impact.
Another related question that I would like to ask, you're kind of more focusing on Monte Carlo with some ingredients of deterministic methods. And there is ongoing question, should we just abandon all deterministic methods in favor of further development of Monte Carlo? Or what is your opinion?
Maybe at the end of my career, maybe I'll give you a different answer, but right now, no. No, you're always going to need deterministic methods because, again, Monte Carlo is excruciatingly slow, and a lot of problems, you don't need high-quality benchmark solutions. You need good enough. So even when you're doing reactors, multi-group MOC works quite well. I mean, we pay for it. Honestly, nodal diffusion, we most of our reactor fleet eyes, we can quantify our bias, we can design codes with this. And we're always going to need quick solutions to get answers as opposed to the elegant continuous energy 3D, which take you the hero calculation. So there's a place for both. So no, let's not stop doing deterministic, please don't.
what ideas do you have for selecting the energy bins for the resonance section?
Oh, geez.
Maybe that's way too complicated of a question.
Yeah.
For right now. Just curious.
Well, so right now, Tim's original approach was basically using optical distance, but it was done in the radial direction for this, where it assumed strong radial dependence and a few other little weird things. Yeah, so the question is, are we going to have to shrink the bandwidth down even more? So are we actually going to have to calculate optical distance precisely? And that takes a lot of computational effort. So I think I know how to get the right answer, but again, it's excruciatingly.
Does it become too expensive to be useful?
And I think the answer is yes, based on what I've seen previously. So we want to do something that's not the precise thing, but still gives us the right answer. So for that one, I don't know. All right. Guess I wore you all out. Thanks, guys.
Thank you.